if you express this in percentage, oh god. Oh, I made a mistake. 1 plus 1 is not 1.98. I should have known. It's 1.99. What the hell am I talking about if I'm saying 1 plus 1 equals 1.98? Is this another like dividing by 0, proving no, it's not gonna be that. You're not gonna reach 1.98 because of that. But what if I write percentage behind the 1? So we have 1% plus 1% equals 2%. It's the same thing. What the? Now that's how normal math works, right? 1 plus 1 equals 2. No matter if it's percentage or numbers. However, if you calculate with probabilities, you can't simply add a 1% probability and another 1% probability, and then it's automatically going to be a 2% probability. Imagine you have two independent events. Imagine you have a 100-sided dice. The chance you roll a 1 on that dice is 1%. Okay? So what are the chances if you roll twice? Do you now have a 2% chance? You have a 1% chance with one throw, and then you have another 1% chance with the other throw. Is the chance that one of those two throws is going to be 1, is that 2%? And the answer is no, it's 1.98%. So why is that? If you calculate with independent events, you can't just add them up. This is not how this works. Which can be easily seen if you have a coin flip and you flip the coin once. You have a 50% chance that it lands on heads. What are the chances that if I flip it twice? Is the chance now 50 plus 50 equals 100% that I will flip heads once if I flip the coin twice? Now this should be obvious that this is not the case. However, with the 100-sided dice, it's not that obvious, and most people will probably say, okay, it's 2%. It's just not how you calculate it. So let me first show you how you calculate it for real, and then we're gonna talk about when to actually use this 1 plus 1 rule and when not to use it, okay? So this is not gonna be very hard maths. You will follow, and it's more about the concept in general. It's just important to understand that it's not addition, it's multiplication actually. So this is just wrong. What we have to do is not addition of the probabilities, but multiplication. If you have a random event, you have to look at what are the chances that the event is not happening. Now, the chances that the event happens at least once in those 2 tries can be seen in another way. What cannot happen if you flip a coin twice? If you flip 2 times tails, then it didn't happen that at least 1 time heads came. Okay, so now we calculate the chance that tails comes up twice. And then the chance of something else happening, everything that is not 2 times tails is at least 1 times heads. So we have to calculate the chance of tails happening twice, and then the rest of the probability is going to be the probability of at least 1 times heads. So how do we do this? Multiplication. If we have not heads and tails, but the 100-sided dice, we have the same thing. We have not a 1% chance that the event happens, but a 99% chance that the event does not happen. And this does not happen has to happen twice in a row in order to be not happening one of the 2 tries. So we got 0.99, the chance that it is not happening in one throw of the 100-sided dice. And then you have to multiplicate this with also 0.99. Okay, so 0.199 is just 1 minus 0.01, which is the 1%. Okay, that's this here. 0.99 times 0.9 equals 1.98? No, that's not right. This here is the chance that the event does not happen twice in a row. So in order to get the probability that it happens at least one, the 1% plus 1% that you actually wanted. Now, what is 0.99 times 0.99 actually? It's 0.9801. That's not 1.98, but if we want the other side of the probabilities, we have to subtract that from 1. Okay, so we got 1 minus this. And what is that? That's 0.0199. If you express this in percentage, oh god. Yeah. It's not 1.98. Okay. It's time to man up and say, I made a mistake. It's 11 p.m. I took 1,000 free throws today, and I'm gonna have to get up in the morning to do another 1,000 tomorrow. And I want to get this video done, so I'm not gonna make it again. And I have to admit, I did that mistake. I don't know where I got this from, actually. Like, how did I come up with that? I had that video idea and I wrote it down, and since then I talked about 1.98. It's not 1.98, it's 1.99. Well, there we go. Anyway, that's how you calculate it. So we got 0.199, and that's 1.99%. If we do this for the coin flip again, so the anti-probability is also 0.5, okay? So we got 0.5, not plus 0.5, which would be 100%, which is not the case. But if you multiply it, you get 0.25. And then if you have 1 minus 0.25, you get 0.75. Just making sure I'm not making a mistake this time again. Oh, so the chance of me flipping at least one heads in 2 tries is 75%. 50% plus 50% is 75% in that term, if you express it in that way, which is not a good expression. And it works if you're not having a coin flip. Now let's say you have a 100-sided dice, or let's say you want to estimate the probability of you dying in one of the next 2 days. And you know the probability of dying at 1 day, okay? The probability of you dying at that 1 day is also somewhat of an estimate. It's probably a rough estimate too. So it's completely fine to actually add those probabilities. If you have like small probabilities and you add them not a lot of the times, like if you have 100-sided dice and you add those 2 probabilities, it's very close to 2. So if you calculate with 2, that's completely fine. But if you throw the 100-sided dice 100 times, then of course it's not 100%. it's 0.99 to the power of 100. I hope you call it that way. Like 0.9 times 0.9, 0.9, 100 times. And then the anti-probability of that. Now what is that? Let me quickly think. The chance of not rolling a 100 times in a row is 36.6%, okay? So the probability of at least rolling 1 at least one time is 73.39 something percent and not 100%. So if you calculate it with 100% there, then you are off, and by a lot. The question is, where is the cutoff? You have to be careful because it is not calculated that way. But in those kind of situations, you can do that. Now let's look at when it gets really, really wrong. If you have a 100-sided dice or you calculate some small percentage, how many times can you add this up? Like, you can't add up the chance of you dying in a day 365 times and then have the chance of you dying in a year. I would be at least careful with that. Maybe with various small probabilities. And if you have big probabilities, like the coin flip, it's immediately wrong. So if you have like a 50% chance, a 60% chance, you just can't add them. But if you have a chance something like 0.999999, and you don't have to have a super hard exact calculation of that, but just a rough estimate, then it's a fine heuristic actually to do that. Just have to be aware that it's wrong and know when you have to actually calculate the real value. So I made an Excel sheet to show you guys how this actually behaves if you put in like different probabilities and add them up over time. So here we got the probabilities for 0.999, 1 in 1,000. Instead of the 100-sided dice, we have a 1,000-sided dice. This is if you add the probabilities like 1 plus 1 equals 2. And this is what the probabilities actually are. Here is the percentage. So you can see the percentage difference. Like this is the mistake you do. You get a difference of 0.01. So 0.999 is very equally-ish to 2, right? And if you do this 20 times, 19.811, still very similar to 20. Now if we go to 995 times, now the difference is actually quite big. Now it actually would be 630, not 995. So that is now a 36% difference. And then I did this also for the 1 in 100,000 chance. The chance of me dying in a day is roughly 1 in 200,000, but let's say 1 in 100,000, okay? Here, if you add those up, the difference between 1 plus 1 equals 2 and the 1 plus 1 probability-wise equals 1.9999 is really, really similar. So you can do this. And here the percentage is still super, super low difference, up to like 30. And then if you go down, it's still, if you do this 1,000 times, you still have only a 0.5% failure in that. So this is actually, if you do this for a year, let's say, you have a pretty good estimate. If you made that mistake and added actually the probabilities up, you wouldn't be much off, even if you do this for a whole year. That's because the probabilities are so small, then you can do it for a longer time. So let's look at how this looks in a graph, okay? Now this is the 1 in 100,000 chance. And as you can see, the difference goes up after 200 tries. We are at 0.1% mistake. And it goes up, it seems linear, but actually it's not. If you look at the percentage mistake, first you add a 0.005 mistake, and then it's not a 0.1 but a 0.999. So you can't add those up either. It actually gets a little bit less each time. Just because the probability is so small, you don't see this in this graph. If we look at the 1 in 1,000 chance, you can clearly see at the graph that it's bending down a little bit. But that's another heuristic that you can actually use for those cases, that the mistake is roughly, it's not linear, but it is close to linear in those cases. Since we're dealing with rough estimates, that's kind of fine, right? If you want to do the exact math, that's not how you calculate this, okay? How much of a mistake do you do per each try you add? So in the 1 in 1000 try, you do a 0.05% mistake each time you add another try. It's not exactly 0.05, but let's say 0.05. What is 0.05? It's 1 divided by 2000. That's percent. So 0.1% would be 1 in 1000. And this is a 1 in 1000 chance. You basically have half of that as a mistake. So this should give you a pretty good guideline on when you can use it, how long you can use it. Maybe you do some maths as an example and then you get a feeling for it when you can actually do it. Because it's much easier to just add the percentage in your head and then you roughly estimate. I do it a lot. As a poker player, you oftentimes estimate probabilities anyway. And then it doesn't matter if you do a 1% mistake. Also with small probabilities. You just have to be aware that you can't do this for a lot of tries or with big probabilities. So be careful when doing it, but it's a good way to do it, but it's wrong.